I'm really hoping that you guys are going to be able to see what I'm doing here. I've got both laptops running. See me. There we go. Right. Good afternoon, everybody. I'm really hoping I'm watching my two laptops side by side once I know that this is all up and running. Yeah, look at that. We're there. This is excellent. Right, and it looks to be running lovely and smooth as well. I'm kind of hoping that the detail, as I've cranked up the settings to make, so it should be on HD. For those people who want to be watching this, because obviously I'm going to be doing pen work, so I'd recommend you switching the settings on your YouTube video to HD. Hey, Ira. Ira, you do not need to be here. This is an AS Chemistry Calculations webinar, and it's, unless you want to sit through it and see these calculations, which you're more than welcome to, but you do not have to be here. But thanks for coming, everybody. Really appreciate it. I'm hoping that you guys are going to be telling me right now that you have crystal clear. Does everyone have crystal clear sound? Is the other chem class meant to be here as well? I told them about it, Julian. I'm not entirely sure whether or not they're going to turn up. I'd love them to turn up. I know that Miss Childs, I think, went through some of the paper with them. I think we realized last time that we got partially through the paper and it was taking an exorbitant amount of time. So I was like, you know what? Let's do this on a webinar. It's far easier. Can everyone just give me a quick shout out to tell me that the sound is good? I am using a brand new microphone that my year 11s bought me as a birthday present, and I'm super excited about trying it. This should be like HD sound. So I'd love to get over thumbs up if it's good. Good mic. Excellent. The microphone was causing so many issues going through my laptop. So I'm really, really pleased that this seems to be giving really good sound now. Right, so what I'm now going to do is I'm now going to turn off my, my screen, and I'm going to share my screen with you guys now. Are we starting where we left off? No. Do you know what I'm going to do, Ben? I'm just going to run straight through the paper. But what I'm actually going to do is I'm just going to do it. You guys saw the fact that I did it with you on the day. And you know what? This paper is hard enough that it's good practice for me to do as well. And I think that this would be a nice opportunity for me to go through. The paper, and essentially what I'm going to do is I'm going to go through it and I'm going to do it myself and talk you through the entire time. That's my plan. Right, so I'm going to switch over to share screen, and I'm hoping that when we drop down to share screen like that, I can now do this. Now I'm going to, I've realized that I'm still sharing. That's the one I want. Winner. Cool, so you guys should now be seeing this. Amazing. Let's just quickly check that. I'm going to click play on this and take that up to, what I'm trying to do now is, there we go. So yeah, perfect. You guys should now be seeing, that's it. Perfect, winner. What I'm doing, by the way, is I'm checking with I've got my MacBook running at the same time so that I can actually see what you guys are seeing as well. I'm now going to pause that video. I'm hoping that it's not going to drain my, switch that right down to that and leave that like that. Perfect, because I've now got the chat window on my MacBook and the webinar, my tablet that I can now write on. Okay, so what I'm going to be doing, I have got my dual screen set up. Absolutely, Julian, I'm going full techno today. It's amazing. So today what I'm going to do on the webinar, I'm going through the paper, but I'm going to flag up all the calculation types. So I'm aiming to be able to say to you at any given point, any question that we hit, we should be able to identify the calculations type immediately. Number two, to recognize the question's level, to be able to see whether or not it's an easy, medium, or hard. And the last one, of course, is to be able to complete multiple choice and long answers. The first thing I thought I'd do is I thought I'd then quickly show you guys the kind of list of the calculations types that we kind of run in chemistry. And I might add to this list as we go through as more of them come into my mind. But these are your main calc types. We've got formulae and equations, percentage composition, percentage yield, percentage atom economy, moles in solids, liquids, gases, and aqueous, which of course now Edexcel in their infinite wisdom make you do for gases. V over 24 is kind of dead because you got that at GCSE. We've now evolved into PV equals nRT, but Edexcel still like to use it. So we might come back to V over 24 in one of the questions. We've then got Avogadro's number and the use of that, followed by empirical formula, molecular formula, percentage error, and reacting mass calcs. So, okay, so first thing, I'm going to crack straight on because I don't want to keep you here. I want to make sure that you guys do as little on this webinar as possible, because I know that if I make them more than an hour, it's not particularly ideal. Okay, so question number 1. Which of the formulae represents the empirical formula of a compound? So this question, of course, is, I would say that this is pitched here as an easy. And which is what I'm actually going to do. I'm wondering whether to make it easier for myself and just put letters next to everything. Because I'm going to use that space to write. So let's see if I can. Oh, my laptop is already having a hiccup. It's running an awful lot, I feel, on it. Maybe I'm going to put easy over here. Easy. Easy. Anyway, sorry. Empirical formula. We know that this is the simplest whole number ratio. This is testing your knowledge of the definition. Whole number ratio. So what we need to have is, we cannot have a number which is a fraction, and we need to say that we cannot divide it to give a simpler formula. Well, for H2O2, we can simplify to that. For C6H12, we can simplify it to this, so it's not that either. C2H4O2 can be simplified to CH2O, so it's not that one. But this one has an oxygen at the number 1. So, of course, A is my answer. Nice, easy start to the paper. Next. Okay, dropping immediately now into PV equals nRT. So we're given, this is, of course, calculations type number 5. The empirical formula one ranks as number 7. That, of course, is a number 7 calc type. Then we're dropping into moles in gases. So we now immediately write down our equation, PV equals nRT. And what it's looking for is it's asking us to work out the temperature. So we're going to reorganize this now, of course, for temperature, which is going to be PV over NR gives us T. Right, now, of course, we've got to do all of our conversions. So now we've got to do, first of all, pressure. Pressure has been given in kilopascals. So we need to immediately do the conversion to 200,000 because it has to go in PV equals nRT as pascals. The volume, of course, is in centimeters cubed. That is not good either. We need it in meters cubed, which is going to be divide by 1,000,000. Now, I like to shortcut it as 10 to the minus 6. I hope that everyone's okay with that. If you want to do that on your calculator, you're more than welcome to do 400 divided by 1,000,000, 1 and 6 zeros. Count your zeros on your calculator if you do that. Right, next we need moles. So how many moles do we got? That was given to us in the question. 0.03 times by R. Notice, they did not in this question give you R. You're expected to know that value. So times by 8.31 is your answer. I've actually got taught when I was doing Abel's 8.314. Let's run that through and see what we now get in Kelvin. So we've got 200,000, counting my zeros on my calculator. I've got 5 of them there. Multiplied by 400 exponential minus 6. I'm actually pressing equals at this point, which gives me now 80. Divided by brackets 0.03 multiplied by 8.31, close brackets. And I get a number of 320. Oh, that's interesting. 320.89 Kelvin. Of course, that will round up to 3 sig fig to 321. And then I go, hang on a second. All of these are in weird units. So I'm going to use the shift eng button. I'm going to go shift eng, and that drops me to 0.32 times 10 to the 3, which means 3.2 times 10 to the 2 is my answer. So that's B. So that's a really clever trick at the end of it. That multiple choice question is actually a level medium. This is a medium. The reason being is it's testing your ability to know your conversions. Second one is knowing the value for 8.31 for your ideal gas constant. And the second thing is to be able to use standard form to give us our output. What a mean trick to do right at the end of that. That is really mean, otherwise known as 3.2 times 10 to the 2 Kelvin. Okay, really clever question though, lovely. Next, which fertilizer contains the greatest percentage of nitrogen by mass? Okay, so this one is just downright hard work. This, of course, is percentage composition, and I would rank it as an easy. However, they're making us do a lot of work here. We've got to work out the percentage of nitrogen in every single one of these. So it's also testing your ability to count atoms. So in this case, the first thing I'm going to do for ammonium nitrate is I'm going to realize that there are 2 nitrogens in this. So I've got 2 nitrogens, of course, nitrogen times 2, which is, of course, 14. So we've got 28. And I'm going to divide what I want, percentage of what I want over the total. So I've got 28, and then I've got, oh, hang on a minute. I've still got the 2 nitrogens at 28 plus, so that's tick him and him, plus 4 hydrogens, which is 4 times 1, plus, so I've ticked him off, plus 3 times oxygen, which is 16 times 3. I'll put that in a bracket. Let's work out that total number. 28 divided by bracket, and so on. No, I'm going to do the bottom number in total. 28 plus 4 plus bracket 16 times 3. Close brackets. Times 3, close brackets. That gives me a value of 80. Let's make that simplify my writings here. That's 28 over 80. So 28 over, oh, don't forget my times 100. It's good practice to make sure that when I get one of these in long answer, I'm still going to end up, so that's with the full marks, that's 35%. Let's do the next one. The next one is, once again, nitrogen times 2. So that's, again, another 28. 28 over, what's my total? So I've got 28 from the nitrogen plus, oh, that's a clever one, 8 hydrogens this time, plus sulfur, which is 32, plus oxygen, which is 16. Now, I'm just going to bear in mind here, folks, if I was doing this on long answer, I would have lost a mark here. The reason being is all atomic masses and molecular masses must be given to 1 dP. So just to be aware, if I was doing this as a long answer, it would be 14.0 times by 2, close brackets, plus 1.0 times by 8, close brackets, plus 32.1 plus 16.0 times by 4. That would be the true long answer version of this times 100. I'm still going to lose the mark because I have told you guys you are not allowed to leave it like this. That there is not allowed. You must run it through. 14 plus 14 plus 8 plus 32.1 plus 16 times 4 gives me 100. So my actual answer in the long bit would be 28. Oh, sorry about that. 28.0 over 132.1 times by 100, and I get 28 over answer, and I times 100, which gives me 21.1%. Next, let's move on to the next one. Each of these I've got to do. I have no choice. Next, diammonium hydrogen phosphate. Let's count my nitrogens. I've got 2 again. This is interesting. I'm seeing 28 reappear. Over total, 28.0 plus 8.0 plus, oh, that's interesting. Another hydrogen sneaking in there as well. So ticked him, plus phosphorus. Phosphorus is 31.0. Oh, 31 phosphorus is actually, I think, 31.1, I think. Oh, check my periodic table at this point. Definitely worthwhile doing. Phosphorus is 31.0. Okay, there you go. So let's go back to this. 31.0 plus 16.0 times by 4. Let's total all that up. 28.0 plus 8.0 plus 1.0 plus 31.0 plus 16 times 4. And I get a value of 132. Isn't that interesting? The same numbers I had before. 132.0 which is going to give me exactly the same number. I'm very happy with that. Makes it a little bit easier for me. Next, right, nitrogen in this. Once again, please notice another 28 appearing. 28 over 12.0 plus 16.0 plus 28.0 plus 4.0. Let's run all those together. Plus 16.0 plus 28 plus 4 gives me a number of 60. So 28 over 60 times 100, it's 60.0, of course. So 28 divided by 60.0 gives me 46.7%. And there's my answer. D, greatest percentage. Done. Yes, guys, it's easy but very hard work. You have no choice there but to do that. Let's keep going. By the way, you'll probably realize that you could have made this a little bit easier for ourselves. We would have, in reality, I eliminated him and him immediately because they're massive. And I was only really calculating these two, but I'd still probably have wanted to have run the whole lot of them just for good practice. Right, next one. Now we get our first really hard one. So this is a hard. 71.0 grams, there we go. 71.0 grams of chlorine reacts with an excess of sodium hydroxide solution at a particular temperature, and the reaction produced 35.5 grams of X. What is the product? Right, let's look at that equation. So we've got chlorine gas reacting with sodium hydroxide. What am I going to make? I've got the choice. So if I make water, well, that's not really going to help us, is it? Water's got, let's, in fact, what are the options that we have here, folks? So now, can I actually point out that there's a whole lot of different methods of tackling this one. And I'm just going to quickly talk through a couple of bits of extra chemistry, which you guys haven't done yet. But chlorine does react with sodium hydroxide. And what you form is a whole series of different products depending on the temperature. So if you do this at cold temperature, what you'll form is sodium chlorate 1, and you're going to also form sodium chloride, and you're going to form water. Let's balance that equation. So I'm going to have 2 here, and then we're going to have oxygens. Oh, the oxygen doesn't add up, does it? I think the water is actually on the wrong side here. Oh, no, maybe not. Oh, am I not getting salt here? I'm not getting salt, am I? I'm just forming sodium chlorate. Let's just run that just to form H2O. Does that, if I double that and double that, that now adds up, doesn't it? No, it doesn't. I still need more water. Sodium hydroxide cold. Sodium chloride plus sodium chlorate. And then they're going to need to balance. We're going to need waters on that side somewhere. 2 chlorines, 2 chlorines, 2 sodiums, 2 sodiums, 2 oxygens, 2 oxygens, 2... Oh, okay, so that now adds up. Fine. Okay, so that is the correct equation. That one is done at cold. Now, it's interesting here because there is another equation, there's another option. I'm going to swing over to here. That's to do with chlorine plus sodium hydroxide hot, which will form sodium chlorate plus sodium chloride. I think now at this point, you add sodium chloride. I think now you actually need to add the waters onto the other side. It's a bit of a nightmare, this equation to balance. And I'm not going to worry too much about it because I'm going to tackle it in a different way. Let's run the moles rather than knowing the chemistry and realizing it's going to be between these guys. What we can do is let's tackle it from a moles perspective. So first thing, let's work out the moles. I'm going to try and zoom out to make this a little bit easier and make my pen smaller. Let's make my pen smaller. Right, so number of moles of chlorine is grams over rams, 71.0 over, and do you notice that the MR, chlorine is 35.5, and we've got 35.5 times 2. Yeah, chlorine is 35.5 on AR, but of course it travels around in a pair, giving us 71.0. So what you'll notice is that it gives us exactly 1 mole. I don't like circling it. It's not particularly nice. Let's just write 1 mole. Right, so that's actually a really lovely thing. So what we now need to decide is, in this particular scenario, I'm going to have a reaction that is going to produce, and do you know what I'm going to do? I'm actually going to erase these equations to give me a bit more space on this. Sorry, my laptop is struggling. I've now got my 1 mole, recognizing that. Right. So let's tackle this from, we've got chlorine going to, by the way, would we agree it can't go to water? Cl's vanished. Let's take it from a sodium chloride perspective. Let's imagine that it was just going to sodium chloride as X and ignore everybody else. I've had 1 mole of this. Well, if we balance the equation for that, number 1 is I'm going to be reacting it with sodium hydroxide to produce that. Well, if I've got 1 mole of this and I was to balance that, I would need 2 of them. And that would produce 2 moles of him. Well, hang on a sec, that's perfect. Let's just imagine that scenario, because the chlorines would have to add up to those. Well, if I produced 2 moles of that, I can now run grams over rams on this. So I've got the mass. This was the important bit. They've given me the mass. I've now worked out that if I put in 1 mole, which is what we did, I'm going to get 2 moles of that out. Let's input that into my equation. So I've got 2 moles equals grams over and sodium chloride, which is 58.5. 58.5. Let's reorganize it, multiply it over to that. And of course, we're going to get a number which is way too large. We're going to have 117. That is not my product. Can't be that guy. Right, let's do the next equation. Can't be that one. Right, I'm going to do chlorine producing sodium chlorate. Now, by the way, this is actually, it's nice to do some proper naming with you guys. This is sodium chlorate 1, Roman numeral. Now, the reason why it's a 1 is because sodium is always +1. Oxygen is always -2, except in hydrogen peroxide. So the chlorine now must be bringing +1 to the party. Hence sodium chlorate 1. Let's balance the equation. For that to work out, I would have to have a 1 mole to 2 mole ratio for the chlorines. Perfect. So what we've got is we put 1 mole of this guy in, and we're going to produce 2 moles of this guy. 2 moles of that guy. Right. Well, I do wonder whether or not we need to factor in the mole ratio from the equation on this. Let's ignore it for a minute. Let's see if it pans out. So we've got number of moles is grams over rams. Well, we're going to reorganize that for rams. And again, we've got 2. It's going to be an enormous number. It's going to be an enormous number. That's not going to work out, is it? Because we've got 23 plus 35.5 plus 16. Total number, 23 plus 35.5 plus 16. Gives 74. 74.5. Right. Well, do you know what? That's an interesting number, isn't it? Getting the MR of that. That's flagged up something to me. Do you know why? I'm looking at the numbers. Ignoring the mole ratio for a minute, I'm suddenly realizing we can tackle this in a different way, can't we? We realize that, in fact, the ratio between the chlorine and the sodium, we don't really know because we haven't got a complete equation. So what I could do instead is simply to say that I'm going to have, suddenly realize that the numbers of the MR is going to flag this. I have got chlorine reacting to produce one of my products in an unknown ratio, in an X and a Y ratio. But what I realized that what are the options I've got? It could be a 1 to 2, it could be a 1 to 1, it could be a 1 to a half, it could be all kinds of different numbers. Well, hang on a minute. What's the MR of this? The MR we just calculated as 74.5. Well, we've put in 1 mole of chlorine gas. Well, is it possible to produce 35.5 grams of sodium chloride? Is it even feasible? Well, 74.5 divided by 2, right? If I divide that number by 2, then I'm going to get 37.25. There is no way I can make 35.5 from that. There is no way I can do it. No matter what the ratio's got to be a whole number. Even if it was a fraction, we're not going to end up with a crazy fraction. This would have to be a bonkers fraction. I can tell you what the fraction would have to be. 74.5 divided by 35.5. I'd have to have a fraction of 2.09, 2.1. I'm not going to have a balancing equation, which is a 2.1. That's not going to happen. What about the last one then? Let's look at the last one. You realize this is to do with ratios of MRs. It's a really hard question. Let's look at the last one. What's its MR? 23.0 plus 35.5 plus 16.0 times by 3. Let's run it through. 23.0 plus 35.5 plus 16 times 3. I get 106.5. Can I make 35.5 from that? Let's divide it by 35.5 and I get an exact number. 35.5 gives me an exact number of 3. So I can do this if the ratio was a 1:3 ratio. So my answer is D. That's really hard. It requires a huge leap of faith, that, folks. That's a really tough question. The only answer can be D. It's the only one that gives us a whole number ratio between the two of them. And as I said, the mole ratio. Oh, do you know what? For fun and games, I'm tempted to write that equation. I'm a bit of a, I just like doing those kind of things. Chlorine, and by the way, I'm going to give myself space on either side. Cl2 plus sodium hydroxide, hot. By the way, this is chlorine chemistry. You will cover it in group 7, unit 2, AS. I'm going to form sodium chloride plus sodium chlorate. Now this one is sodium chlorate 5 is what that is. That is sodium chlorate 5, Roman numeral, because the chlorine's at a +5. Right, let's balance it. Right, 2 chlorines, 2 chlorines. 1 sodium, 1 sodium. Oxygens doesn't add up. Right, so I'm going to probably make water as an output here. So, because we also need hydrogens. Let's put water over here. Right, so now we've got 2. Let's double this one. Oh, let's do this via oxidation states instead. Otherwise, I'm going to be here for a while. I don't like running this as a standard GCSE balance. I prefer to do it the other way. The only thing that is changing oxidation state is chlorine. And this reaction, so does that mean that the ratio will always be a whole number? Yes, Ben, whenever you balance an equation, I know that you guys balance with halves, but you can always multiply the equation up to give you whole numbers within it. You're never going to get to a 0.1 because then you'd have to multiply it up by 10 to get it to a whole number. You never get there. It's going to be a simple ratio between the two of them because you can't have 0.1 of an atom. So yeah, it will be. Right. This is called a disproportionation. Disproportionation reaction. That word means that the same species is being simultaneously oxidized and reduced at the same time. The oxidation state, the charge on chlorine here is 0. The charge on chlorine in sodium chloride is -1. The charge in chlorine over here is +5. So we can break it into its half equations. So we've got chlorine is going to go to sodium chloride. By the way, I'm going to ignore the sodium and just go to chloride because the sodium is a spectator ion. It's not doing anything. Balance the half equation. It's going to need to gain 2 electrons. Next, I now need chlorine to go to chlorate, and that is ClO3-. People often ask me why the oxygen doesn't disappear. Well, that's tricky on that because the oxygen doesn't change state either, but it's covalently bound, so it can't be separated. The sodium ion is floating around in solution, not doing anything, whereas the oxygen is actually physically bound to the chlorine itself, so it needs to be incorporated. So the first thing we need to do is balance for chlorine. By the way, I will teach you this in redox. The process I am running here is MOE, which is the metal. There's the M stands for metal in this case, but there's no metal here, but there is chlorine. So the metal in this case is chlorine. So I'm going to balance for that first, hence the 2. Now the W stands for water, which is actually there for oxygen. So I've got 3 oxygens here, so I'm going to need 3 waters over here to give me oxygens. Tick. Now I need acid, and the acid provides me with hydrogen. So how many hydrogens do I have? I've got 6 here. I'm going to need 6 H pluses over here. 6 H plus. Now I need electrons. Now I've done that guy. Now I need electrons is my last one, E minus for charge. So I've got 0 on this side, 0 on this side, but I have -2 from here because I've got 2 of them, and +6 from this guy. Total, of course, is going to be +4. So I need to get from 0, because this was 0 and 0, hence 0, -2 +6, 4. I need to add 4 electrons to this side. I need to add 4 electrons. Let's get rid of that. I need to add 4 electrons to this side to balance it. Right, now I can now start looking at putting the equations together. The problem is I need to balance for charge, and to do that, I need to balance for electrons. So I've got 4 electrons needed here and 2 needed here. Right, multiply this top equation by 2. Give me 4 there, 2 and a 4. Right, and I now have the numbers I need for my equation. The electrons cancel. What else disappears? Anything else? Nope, chlorines add together. So I'm going to need 4 sodium chlorides. There's that guy. I'm going to need 2 sodium chlorates. I'm going to need 3 waters over here. 3 waters over here. That does this guy, and this guy. I'm going to need a whole load of chlorines. I'm going to need 3 chlorines. Let's add that in. Right. And now balance for the sodium hydroxide, because that's got another reaction going on. So I've got 6 hydrogens. Nope, more than that. Ooh, hang on a sec. Where are my hydrogens? Where's my acid? Oh, it's in alkali. It's in alkali. Sorry, folks. This is, by the way, I've gone way OTT on this. I've suddenly realized do you notice there was a problem? It didn't add up. I didn't have everyone there. The reason being is because the condition here is alkali, but I'm balancing in acid. Can't do that. Need to convert the second equation. Let's convert it to alkali. H plus reacts with OH minus to form water. I need to get rid of 6 of them, so let's multiply this by 6. Don't worry, I'm going to be teaching you guys this when we get to redox. Cancel that and that. Right, anything else disappeared, the water does. The water disappears, 3 of those waters vanish, 3 of those vanish. Right, now I can put the numbers in. So I've got 6 sodium hydroxides and 6 waters on that side. So I've got 3 waters over here. And then I go, how many sodium hydroxides was it? 6. And this should now add up. So I now have, let's check it. Check all the way through. Whenever you do these complicated balances, you always check it through. I've got 2 chlorines. Oh, hang on. Did I just delete that number by accident? Yes, I did. 6 chlorines here, and I have 6 chlorines over there. That's always nice. Adds up. Next, I have got 6 sodiums. 6 sodiums. Adds up. I like it. Trying to get rid of all my little lines. There we go. 6 sodiums. 6 oxygens. Ooh. Am I out still? I'm still out. It's not going to work. Ooh. Nightmare. I've got too many oxygens. How have I got too many oxygens? Ooh. I've got too many oxygens. I've got 6 oxygens here, but then I've got more over here. I've got 6 plus that's 9. It doesn't add up. Oh, where have I gone wrong? Oh, hang on a sec. I didn't balance for the waters properly, did I? Look, so it's nice to flag it, guys. Everything comes out in the wash. Look, when I was balancing for waters, I balanced it with the number 3. I shouldn't have. I needed 6 of them, not 3. That needed to be 6. What that means is they completely cancel with those guys. So the water is going to vanish. But then hang on a minute, my hydrogens won't add up. This is entertaining, isn't it? 3 chlorines, 6 chlorines, 6 chlorines, 6 sodiums, 6 sodiums, 6 oxygens. Now I have 6 oxygens, but then I have 6 hydrogens, and there is none. I don't know why. Sodium chloride, sodium chloride. I've got acids. Oh no, the acids vanished. Where have they gone? Oh, hang on. If I balanced that there, I needed more there. Oh, this is the problem when you try and fix stuff, folks. I'm sorry. That then becomes 6 12H pluses, which then doesn't cancel out, which means I need then 6H pluses on the... Oh, I needed to convert that better. Oh, I needed to multiply that by 12. Oh, nuts. That then becomes 12. That then becomes 12. Those 6 cancels out with 6 of those. So it will, or it still comes out in the wash. So those 6 cancel out with those 6. But now I need 12 sodium hydroxides instead of 6 of them. Oh, hang on a sec. This is what happens if you make a mistake and trying to fix it is a nightmare. I'm tempted to do this again because this now, I'm going to start again. I'm sorry, folks. I know you're thinking that we've got the rest of the paper to go through, but I don't want you to think that this is unbalanceable. Do you know what? I'll come back to it at the end of the paper and you guys can then switch off if you want to. How many molecules are present in 16 grams of oxygen? Avogadro's constant. Okay, so we know that number of moles is grams over rams. This goes into a nice easy. Thank goodness for that, eh? I shouldn't have gone into balancing it in the first place. 16 over 32.1 in your, if you did this long answer, you'd lose it if you've got the 1. That's going to give us, of course, half a mole. So we've got half a mole of oxygen gas. Well, hang on a minute. We also know that 1 mole equals Avogadro's constant, 6.022 times 10 to the 23. Right, so multiply that by a half. And I'm going to get 3 times 10 to the 23. It's D. Moving on. Oh, Naomi. Thanks, Naomi. Naomi's balanced it for me. Thanks, Naomi. Oh, no. Naomi, the chlorates. Yeah, okay. She's put the star there. Yeah, fine. I will have another go at that at the end. Next, right, another horrible question. So this one is making us look at different options. A student makes sodium chloride by reacting 0.025 moles of sodium carbonate with excess of 0.2 molar hydrochloric acid. Which statement about the quantities is true? Right, so that's telling us that the hydrochloric acid is in excess. So the sodium carbonate, let's write that underneath the bottom in moles. This is mole. Right, next, so in a 2, that's a 1 to 2 ratio. So double it. I have 0.05 moles of that, 0.05 moles of that, 0.025 moles of that, and 0.025 moles of that. Right, it says 600 centimeters cubed of carbon dioxide is produced at room temperature and pressure. Right, so what that means is I'd have to use PV equals nRT. Let's check it. So PV equals nRT. And what it's looking us to check is the volume. So let's reorganize for that. Right, moles we now know is 0.025 multiplied by 8.31 multiplied by the temperature of 298, all divided by a pressure of 100,000. And I get a number of 6.19 times 10 to the minus 4, but this is in meters cubed. So what we now need to do is multiply that by 1,000,000. And I get 620. Ooh, 620? That's really close. Now, hang on a minute. It would suggest that number 1 was wrong. That's what it would suggest. But we'll come back to it. Next, 250 centimeters cubed are needed to exactly neutralize it. Over 1,000. Let's reorganize for volume. Times by 1,000, all over the concentration of 0.2. Right, so moles was 0.05 multiplied by 1,000 divided by 0.2. And I get 250. Number 2 is correct. So if one is wrong, then it's got to be one of these guys. Next, 1.46 grams of sodium chloride is done. Okay, so there's the moles, grams over rams. Number of moles is grams over rams. The rams of sodium chloride is 23.0 plus 35.5, which is 58.5. Reorganize 58.5 multiplied by 0.05, which is the moles, and I get 2.9 grams. Number 3 is wrong. Right, hang on a minute. Number 3 is wrong. So 3 is wrong. 1 is wrong. That leaves nobody. Lol, no answers fit. So at this point, we go back to the first one. V over 24. V over 24, let's run it. Number of moles equals V over 24. That's in dm cubed as well. So reorganize. So the moles of carbon dioxide, which is 0.025, multiplied by 24, gives us 0.6 times by 1,000, and I get 600. So 1 and 2 are correct. The answer is B. Horrible at Excel. Next, in ideal gas equation, PV equals NLT, the units of N and T are, well, N's is moles, so it's either C or D, and temperature is always in Kelvin. So the answer, of course, is D. We're done. Nice, easy one. Moving on. Number 12, 1.15 grams of a metallic element needs 300 centimeters cubed of oxygen to completely react at this to form an oxide which contains O2 minus. Right, okay, fine. So we've got 1.15 grams of either a group 2 element or a group 1 element. Well, at least I know what the formula is going to be. So it's either going to be, let's call it X, let's call our metal X, reacting with oxygen to form a group 2. Let's then balance it. Or that would tick off the top 2. Or the bottom one, which would be reacting with O2 to form X2O. Let's balance it. Okay, so it's either a 1 to 2 or 1 to 4 ratio. Let's work out how many moles of oxygen we've got. PV equals nRT. Now, they've done something odd here, guys. They've given it in atmospheres. They should never do that anymore. But let's run that through. We need to reorganize for moles over RT. Right, pressure is 1 atmosphere, 101,325. I'm going to use that one, even though I'm actually should be using 100,000, because you guys would just know it as 100,000. Stuff it. Let's use 100,000. 100,000 multiplied by the volume, but it has to be in meters cubed. There's a conversion, times 10 to the minus 6. All over 8.31 times by temperature of 298. Let's run that through. 100,000 multiplied by 300 exponential minus 6 divided by brackets 8.31 multiplied by 298. Right. Oh, okay. So I get 0.0121 moles of oxygen gas. Cool. If I'd used the other number, no, I don't know, let's just leave it at that. Okay, so we've now got moles of oxygen. Right, so we can put that here. So that's going to be 0.0121, 0.0121. So if it was a group 2, if it was one of the top 2, then it would have to be in a 1 to 2 ratio, which would give me the moles of this, 242. If it was a group 1, it would have given me moles of 0.0484. Right, let's check those numbers through. So if it gave me that many moles, I can now do number of moles as grams over rams to work out what the rams is to identify my element. So times by rams, get rid of it, and then bring moles down. Right. So rams equals grams over moles. So I've got 1.15 grams divided by 0.0242. And I get an atomic mass for a group 2 metal of 47.5, which does not fit either of them. Calcium is 40.1 and magnesium is 24.3. It is neither of them. It's not even close. Yeah? Next, let's check it for a group 1 then. So now we do 0 grams over moles, 1.15 divided by 0.0484. and I get a number of 23.7. Right, and of course we know that sodium is 23. It's really close, which of course means it is sodium. There's going to be a number that they're using something odd here. I'm really curious to know if I put in 325. I'm really curious to see what that does. 101. It's just really weird for them to quote 1 atmosphere times by 300 exponential minus 6. Oh, hang on. 101,325 times by 300 exponential minus 6 divided by brackets 8.314 multiplied by 298, close brackets. And I get a number of 227 actually. 227, multiply that by 4, gives me that number, grams over moles, 1.15 divided by answer, gives me an MR of 23.3, which is then really close to sodium. So sodium's the only answer there it can be, because the other one is miles away, whereas that one's hit it to 1 decimal place. Sorry, so a whole number of 23, so it's going to be sodium of D. Next, right. That was, by the way, another hard, really hard question. Next, magnesium nitrate decomposes. Right, this was the hardest question on the paper by a mile, because unfortunately, in order to choose between certain people, you had to know the equation. So group 2 nitrates like magnesium nitrate, Mg brackets NO3, go through thermal decomposition to form MgO plus NO2 plus O2. Balance the equation, which is going to give me 1 Mg, 2 nitrogens, oxygens, which is then going to spit me out as a half there. So that's what's happening here. And it says there, magnesium nitrate will compose to give a white solid, which was magnesium oxide, and a mixture of gases. One of the gases released as an oxide of nitrogen. Now, guys, at this point, it's really hard. If you didn't know this, you would have been picking between 2 numbers. But in this case, you have to recognize that nitrogen monoxide is very difficult to make. Nitrogen dioxide is the more stable of the two. You always go for the more stable. So it's the example is SO2 and NO2 are always the ones that you'll always use in any exam. NO is very unlikely. It doesn't last very long. Right, it then says 7.4 grams of the anhydrous salt is heated, and it says until no further reaction, what is the mass of X? Right, so it's going to be X as the nitrate is NO2 here, so we can then say, well, we need to convert this to moles, don't we? In order to use this equation, we need moles. So I need to work out its MR, 24.3 plus 6 plus 14.0 times by 2 plus 16.0 times by 6. Right, let's run it through. 24.3 plus 14.0 times 2 plus 16 times 6. And I get 148.3. 7.4 over answer. And I get moles of 0.0499. Right, it's in a 1:2 ratio. So double it, and I get 0.0998. Multiply that by the MR of NO2, which is 14.0 plus 16 times 2. So multiply that by 14 plus 16 times 2 gives me 4.6 grams. And my answer is there, of course, in my choices as D. Hard that. Just got to know that one you had to have a bit of knowledge of. Sorry about that, folks. Next, what is the ionic equation for the reaction between sodium carbonate? Right. This is me doing a little bit of a lesson on ionic equations, by the way. Ionic equations is an equation showing which ions are actually doing stuff. You're going to delete spectator. So sodium, group 1 ions never do anything. They're very stable. So it's the carbonate ion which is actually doing the reaction. Nitric acid, of course, is HNO3. And of course, the nitrate ion is not going to do anything either because we're going to form sodium nitrate. So we're going to have H+. We're going to need 2 H pluses for every carbonate ion. So the answer, of course, is going to be B. Next, use the relevant data book, otherwise known as your periodic table. Right, next. So, the reaction between aluminium powder and anhydrous barium nitrate is a propellant, yada, yada, yada. What is the mass of barium oxide, question mark, produced when 5.4 grams of aluminium powder, so it's given me 5.4 grams of it, react with excess barium, right, so that's in excess, so we can ignore it. So grams over rams, that's over 27.0 for aluminium. Let's just check my number there. I always like to check if I'm not 100% sure on my aluminium, 27.0. So grams over rams, 5.4 over 27 gives me moles of 0.2. That's a really nice flag, which tells me I'm going in the right direction. The ratio, of course, is 10 to 3. Divide by 10 times by 3 times by 3 gives me 0.06 moles of him. How much does barium oxide weigh? No idea what barium weighs in the periodic table, hardly ever use it. Barium weighs 137.3, 137.3, multiplied by my moles of 0.06, and I get a mass of 8.23 grams. Ooh, I've made an error. It's not there on my thing. What have I done? Let's check that, shall we? What mass of barium oxide is produced when 5 grams of aluminium powder? That's fine. Okay, let's try this again. 0.2 divided by 10 times by 3 definitely takes me, so that is correct. Did I work out? Oh, I haven't. Oh, I'm an idiot. It's barium oxide, isn't it? Got to add on oxygen. Oh, so 100 and what was it? I missed that bit. 137.3, 137.3 plus 16.0 gives me 153. Excellent. So times that by 0. So that is the mass of this is 153.3. Multiply that by 0.06 moles. And I get a mass of 9.18. And there's my answer, C. Let's move on. Next, combine the equations. The following half equations occur when potassium iodate and hydrochloric acid is oxidized to iodine. Right, in order to combine them, you cannot have electrons left over. So we've got to multiply this bottom equation by 2. So I'm going to double this. 8, 4, and 4. Cancel out what cancels. That cancels. Anything else? No. So let's now put those together. So I end up with an overall equation of, I'm going to do it over here, IO3 minus, that's that guy, plus 2 iodines, plus 2 Cl minus, plus 6 H pluses, plus, oh, isn't that nice? They're going to add together. Look, those add together to become 10. So I can erase that and replace that with 10 Cl minuses, all going to ICl2 plus 3 H2Os plus 4 ICl2 minus. Running out of space. Right, what's the ratio between iodate and iodine? It's 1 to 2. B. Next. During steel making, impurities are removed by, what is the ratio between them of calcium oxide and phosphorus pentoxide? I like it. Had to write an equation. So P4O10 plus, is that what we needed? Yeah. Plus CaO goes to, and they've given us the formula, which is rather nice of them, calcium phosphate brackets PO4 brackets 2. Cool. Balance the equation. 1 phosphorus, 4 phosphorus, multiply that by 4. 4 phosphorus, 4 phosphorus, 10, 11 oxygen. Oh, let's do the calciums first. Lots of them. 12 calciums, 4 times 3, 4, 8, 12. Oh, I've made a mistake already. I've already made a mistake. Hang on. Can't rush these things. 4 phosphorus, 2 phosphorus. Double it. Right. So I've now got 4 phosphorus now. There we go. Now we can do the calciums. 6 calciums. Oh, 6 calciums. Check my oxygens. 10, 16. I've got 8 here times by 2, which is 16. It now balances. The ratio between those two is going to be a 1 to 6. How many moles of calcium oxide react with 1 mole? The answer is D. I like it. Next. Right, now my printout did something really weird. It moved a couple of pages, so I'm going to continue with the multiple choice. When 0.635 grams of copper reacts with silver nitrate, this much of silver is produced. What is the ionic equation? Right, well, can I just point out, guys, you don't actually need the numbers to do this. If you know your numbers, which you should, number 1, silver is always +1. Always. So which means it is either B or D. Right, the next thing is copper never forms +1. It always forms +2, except in the Fehling's chemical test. It's the only time it forms a +1. So the answer, of course, is going to be D. But we can check it, can't we? Let's check this. So we've got grams of copper. So I've got copper metal reacting with silver nitrate. Silver nitrate to produce silver, Ag, and copper nitrate. We can check this. Balance it. 2 of those and 2 of those. Right, I've got 0.63 grams of copper. That's no use to me. Need it in moles. Oh, look, do you notice? Yeah, so grams over rams, 0.635 over 63.5 gives me 0.01. 0.635 divided by 63.5 gives me 0.01. Right, if, let's have a look at this. If it was this guy, it would be a 1 to 1 of that. Yeah, which means I'd make the same moles. Well, times that number by the MR, which is 107.9. So times that by 107.9, and I get 1.079 grams, not the top one. Next one, copper solid going to Ag. It's still the same 1 to 1. Can't be that one. Oh, the only one with the 1 to 2 to silver is D anyway. So it confirms, let's check it. So if I had 0.01 moles of that, the ratio, of course, is a 1 to 2. So I get 0.02 moles of that. Multiply that by the MR or AR of silver. Multiply 0.02 times 107.9. And I get a mass of 2.158 grams. So it's D. Next. Right, the concentration of blood glucose is usually given in millimoles per decimeter cubed, or millimoles per dm cubed. A reading of 5 within the normal range. Glucose has a molar mass of this. What mass of glucose dissolved in 1 liter of blood would give a normal reading? Right, so number of moles. Oh, this is cool. Number of moles is C times V. Now, I don't need the 1,000 here. The reason being is because the volume has been given to me in decimeters cubed. So I can just leave it as C times V. That's nice. Now, my moles, yeah, it tells me that the concentration of within normal range is 5 millimoles per liter. 5 millimoles per dm cubed. Well, hang on a minute. I'm working, my moles is just moles, not millimoles. So I need to convert millimoles to moles. Milli is 1,000th. So I'm going to divide this by 1,000. That is the same. Divide that by 1,000, and I get 5 divided by 0.00 shift 0.005 times by 1 gives me a moles of that. Yeah, because all I'm doing is running that through my equation. That's the moles, not the millimoles of glucose needed for within normal range. Let's put that into the hang on, this is moles. Oh, look, that's the moles. Let's put, oh, hang on a sec. No, this is a concentration. It's not moles, is it? That there is moles per dm cubed. Wait, hang on a second, but we've got 1 liter. So if I run that number of 0.005 times by 1 gives me a moles of the same number. So that is also the moles. Right, they've given me the MR. Number of moles is grams over rams. Reorganize for grams, bring the rams over. So times so times by rams, which is 180 times by 0.005, multiplied by 180, and I get a mass of 0.9 grams. There we are, C. Next, which of the following, Ben, sorry, Mr. Duncan, I gotta go, but I'll watch the rest of the webinar when I go back. Thanks again for your time. No problem, Ben, you're very welcome. Which of the following species contains the same number of electrons as neutrons? Oh, that's cool. So this is just a simple atom breakdown. So boron contains 5 protons, 5 electrons because it has no charge, and it also contains 6 neutrons. Electrons and neutrons. Nope. Next, holy moly. Door slamming. 11 protons. Oh, it's lost one. 10 electrons and 12 neutrons. Definitely not the same number. Magnesium, 12 protons, lost 2 electrons, 10 electrons, and 12 neutrons. Not that guy either. Fluoride, this has 9 protons. It has 10, oh, hang on. It has 10 electrons because it's gained 1, and it has 10 neutrons. So it's D again. Lots of D's appearing on this paper. God, if you didn't know and you were guessing B, you'd be stuffed. The recommended limit of sulfur dioxide in the air is, I love how they've given us it as a percentage, and they want it in parts per million. So the question is, what is my million? And the answer is 100%. 100% is the bigger of what that number is. It's my million. Yeah, so 100% equals my 1 million. So how do I now get from 100 to 1 million? If I want to get that, I'm going to do 1 million divided by 100 gives me, it is a times by 10,000 factor. So I need to times my percentage by the same number. This is my smaller, this is my percent that I had. How do I get that to the millions? Do the same multiplying factor. So I'm going to multiply that by 10,000, 0.00025 times by 10,000, and I get a number of 0.25, so the answer was B. So that's the end of the multiple choice. They were hard, really hard. Long answers are easier, folks, always easier. Let's run them. Right. How are we doing time-wise? It's 1 o'clock, we've done nearly an hour. Okay, the sample of boron oxide was reacted with carbon and chlorine. Okay, calculate the mass of boron oxide reacted. That reacted. Okay, so they want us to calculate the mass of the boron oxide. There's my question mark. But what they've given me is all the thing of the gases. So it says, complete with the carbon and chlorine, the 2 gases produced. Right. Oh, this is clever. So it's given us the total volume of gas. Yeah, so we can now do PV equals nRT. PV equals nRT. Let's lob in my numbers. I need to reorganize for moles, of course. So therefore, moles equals, bring that down, PV over RT. Input my numbers. So therefore, 100,000 times by a volume of 5,000. It's in centimeters. Got to get to meters times by 10 to the minus 6, all over 8.31 times by a temperature of 298. Here's my moles of gases, 100,000 times by 5,000 exponential minus 6 divided by brackets 8.31 times 298. Checking my numbers on the calculator, I missed the 8. Gives me a number of moles of total gas of 0.202 moles. Right, 1 mark there, 1 mark for all my conversions, 1 mark for my moles. What is the ratio of total gas? 2 of that and 3 of that? It is a 5 to 1. That's the leap of faith there, folks. This is a 5 to 1, so we need to divide by 5. So 0.202 divided by 5 gives me 0.0404. It's actually 38, just so you know, but I'll leave it at that. 4 moles. Right. I need to now know its MR to work out its mass. It asked for mass, didn't it? Yeah. Boron oxide. We need to look up boron. Oxygen, of course, is 16. Let's find boron. Boron has a mass of 10.8. Right. So B2O3, yeah. So 10.8 times by 2 plus 16.0 times 3 gives me, I'm going to do grams over rounds times by, multiply that by brackets, I'm going to lose the mark, 10.8 plus 10.8, 10.8 times 2 plus 16 times 3, keep missing 16 times 3, gives me 69. There's a mark in my exam. Yeah, everyone's going to miss it. Times that by that number, times by 0.0404, and I get a mass of 2.81 grams. And there's my final answer. Next. Boron trichloride is easily hydrolyzed to form two different acids. Calculate the concentration in moles per dm cubed of the hydrochloric acid produced when 34 is added to 500 centimeters cubed of water. Right, so they want the hydrochloric acid and they want its concentration. Number of moles is C times V over 1,000. Why over 1,000? Because I'm in 500 centimeters cubed. Now I've been given grams of boron trichloride, which is going to be 43.2 grams. I need moles. So number of moles is grams over rams. I need to use both equations. So I've got 43.2 over, need to work a boron was 10.3 plus 35.5 times 3. Got to work out that number for a mark. 10.3 plus brackets 35.5 or 35.5. I missed the 5 on my calculator. Easy calculator errors. Always look back at what you're doing. Gives me 116.8. That is a mark. So 43.2 over answer gives me a moles of 0.369. It actually gets rounded to 370 moles. What's the ratio? The ratio, of course, is a 1:3. So let's multiply that by 3. So times by 3. I've kept that number on my calculator, which gives me a moles of HCl moles as 1.11 moles, rounding 3 sig fig. Right, I now need to put that through C times V. I've got moles now of 1.11, times it by 1,000, bring it over, and then divide it by the volume of 500, and I get my concentration, times by 1,000, divided by 500, and I get a concentration of 2.22 moles per dm cubed. And there's my answer. Next, any questions so far? Nope, doing okay. Next. Right. An unknown metal carbonate. Oh, it's always clever, isn't it? Right. Tackle it step one at a time. Calculate the moles in HCl in. So this is a nice straightforward C times V over 1,000 because I'm in centimeters cubed. Therefore, concentration is 1.5 times by the volume of 33.2 all over 1,000 gives me 0.01. Easy to do that. 0.15 multiplied by 33.2 all over 1,000. S to D gives me 4.98 times 10 to the minus 3 moles. Next, so it then says calculate the moles of that reacted with this moles of HCl, give your answer. So with this moles, right, so hang on a minute, that's HCl. Let's write that number there. 4.98 times 10 to the minus 3. Oh, look at the ratio. So there's the first mark. It's a 1 to 2, it's a 2 to 1 ratio from where I'm traveling from. 2 to 1 ratio, I'm traveling this way, divide by 2. So my answer is simply to divide that number by 2. Divide the number by 2 gives me 2.49 times 10 to the minus 3 moles. That reacted with that. Right. Calculate the mass of the Mg in the right. This is clever because look, they took 3.44 grams and they dissolved it into 250. And then they took a 25 centimeter sample. So they only took 1/10 of it. So I now need to multiply to get back to my original. I need to multiply this by 10. 2.49 times 10 to the minus 3 times by 10, of course, gives me 2.49 times 10 to the minus 2 moles. Done. Calculate the relative mass. Right, we've got grams, we've got moles. Number of moles is grams over rams. Reorganize for rams. We want the rams. Bring the moles down. Grams over moles. So 3.44 grams divided by the moles of 2.49 times 10 to the minus 2. So I just go 3.44 divided by answer, and I get a mass of 138.1. It's actually 0.2 when it's rounded. So there's my answer. Hence deduce the metal M. Right, so I just need now, that is the total mass of all of it. Let's get rid of all the people I know. So I'm going to get rid of over here, I'm going to go 138.2 minus 12 for the carbon atom, minus 16 times 3 for the oxygen atoms, and that will leave me with 2 M's. So I'm going to do minus 12.0 minus 16 times 3, which gives me then 78.1, but that's 2 M's. That's 2 M's. So divide that number by 2 to get me 1 M, and I end up with 39.0. So the AR was 39.1 actually is how it's rounded, which of course is potassium. Identify the metal, K brackets. Oh, does it ask for symbol? No, doesn't. It could do either. Potassium. Next, boric acid. This is question number 5C. Boric acid can react with sodium hydroxide to form sodium borate. Write an equation. Right, this is checking your ability to create formulae. They've given you boric acid. They're asking you to add sodium hydroxide. And what you have to do is figure out that the borate ion is +3. So we're going to have sodium borate. And of course, this is quite a nice one because the H is +1 and A is +1. So they're just going to do a flat out switch. It's going to then, of course, form water. And then you have to balance it. And I think that probably works. Yeah, there you go. Next, boron trichloride can be reduced by using a hydrogen to form pure boron. That's a dangerous exercise. You're using a hydrogen gas. All right. And you're producing hydrochloric acid. Not the best, but okay. Calculate the percentage atom economy for the formation. Oh, I like it. So percentage atom eco. So we have the desired atom. So we are just making one boron. Boron over total out. So we've got boron plus 3 HCl's. 3 HCl's. Let's put some numbers in here. I'm going to actually make my pen a bit fatter now. So I've got, there we go. So I've got boron. How much did boron weigh? 10 point, oh yeah, we know these numbers, 10.3 now. Over, you see, you picked them up pretty quick. Plus, which is now, we need to sum that up. 10.3 plus, oh, how many hydrogens are there? 3. Plus 3 plus how many chlorines are there? 3. Plus 35.5 times 3 gives me 119.8 times 100. Oh, the percentage atom economy is shocking. Over answer times 100. Holy moly. 10.3 divided by 119.8 times 100 gives me 8.5, rounds up, 8.60%. That's shocking. One way the company producing boron could increase its profits, sell the HCl byproduct. Byprod. Nice and easy. Next. A different compound of boron and chlorine has a relative mass of this and contains, work out empirical form. Molecular. Ooh, you've got to go to empirical and then remember to multiply it up. That's quite clever, like that. So this is boron and chlorine, so B and Cl. Right, the percentage of boron was 13.2. 100 minus 13.2 gives me 86.8. Change the percent sign to gram signs. Divide that by 10.3. Divide that by 35.5. So I can go 86.8. I've already got it on my calculator, so I may as well use it. Divided by 35.5 gives me 2.45. Then I do 13.2 divided by 10.3, which gives me 1.28. Divide them all by the smallest, 1.28 over 1.28. That gives me a number of 1. 2.45 divided by answer gives me 1.91. Ugh. That's not very nice, is it? Not very nice at all. Oh, hang on a minute. Let's assume 1 to 2 then. This is clever. Let's assume 1 to 2 for empirical, which would be BCl2. Well, hang on a minute. They've told us the real thing is 163. Let's see if it's a multiple. Because 10.3, that there is going to have a mass of 10.3 plus 35.5 times 2. 10.3 plus 35.5 times 2. That's going to give me a number of 81.3. Is that a multiple of that guy? 163, so 163.6 divided by 81.3. 163.6 divided by answer gives me an exact number of 2. Amazing. So the real answer is B2Cl4. And I'm done. That's clever, that. That's really sneaky. It's almost a times 10. I don't like it. It's horrible. They're being mean. Maybe my rounding errors have added up. Possible. Oh, we're at the end of the test at 1 hour and 15 minutes. Oh, that has been hard work, folks. Oh, I am not done. No, I'm not. I'm doing this again. I'm gonna start from complete scratch again. Sorry, folks, I've got to do it. It will bug me otherwise. Chlorine gas reacts with sodium hydroxide to form sodium chloride and sodium chlorate. 5. Right, the half equations. Got to remember that they both need to be an alkali. Cl2 going to Cl minus. Double it, 2 electrons. Easy, easy, easy. Next, Cl2 going to ClO3 minus. Yes, okay. So now we need to double this first to give them the chlorines, then waters, which is 6 H2Os because I need 6 oxygens. Now I need lots of hydrogens, which is going to be 12 H pluses. Now I need to balance for charge, which is going to be plus 10, because that's minus 2, that's plus 12, so it's going to be minus 10, and that's 0. I need 10 electrons. Ah, that's why. There's my 10 electrons. Right, but I can't do that yet. What I must do is convert to alkali first. Right, because now I've balanced it in acid, I need to convert. H plus OH minus goes to H2O. I've written this way round so that the H pluses cancel. I need 12 of them. So I'm going to cancel that out with that. What waters vanish? That vanishes to leave me with 6. Right, now I can put the equations together, but I need to multiply this one by 5 so that the electrons cancel. That's going to give me 10 of those, and whoa, 20 of the, oh, no. No, what have I done? Ruined this again. 2 times what is 10? 5 of those and 10 of those. Right, now I can put them together. Okay, electrons cancel. Whew. Hang on. Oh, what have I done? Put the electrons on the wrong side. I am not doing this very well today at all. So funny. Email you the timings. Yes, please, Winkit. That would be great. Right, electrons cancel. Put the electrons on the wrong side when I balanced it, didn't I? It was plus 10 and 0. I needed to bring that down. They cancel. Thank you. Water's cancelled. Now I can put them together. So let's look at my equation. I'm going to need 6 chlorines. I'm going to need 12 sodium hydroxides. I'm going to need 10 sodium chlorides. 10 sodium chlorides. I'm going to need 2 sodium chlorates. And I'm going to need 6 H2Os. Let's now check it. Come on. Come on. 12 chlorines. 12 chlorines. 12 sodiums. 12 sodiums. 12 oxygens. 12 oxygens. 12 hydrogens. 12 hydrogens. There's my correctly balanced equation. Yay, I finally did it. All right, guys. Let's see if I can bring you guys back. Let's see if I can bring you back. Back to here and go stop screen. And I should be back, folks. Hello. Hey, guys. Right. Thanks so much for coming, guys. I really, really appreciate it. I know it's been a long webinar. It's been an hour and 20 minutes, but I think you'd agree, totally worthwhile going through. It was not an easy paper at all. If you've got any additional questions, please let me know, and I can do it with you then in school. Guys, I hope you have a lovely rest of your Saturday. I'll see you all soon. All right, bye, guys.